Welcome back, guys. So in this lecture we are going to see about vector spaces. As you can imagine it to be a space where your vectors live. So what are basically vectors? We have seen in the previous lectures and all that vector is a quantity which has both magnitude and direction. So in data science, have you ever wondered like what your data, what your features really looks beneath the surface? So the answer is it is basically represented as a vector. So not the rows and columns in your spreadsheet, but what those rows represent mathematically. Okay, so each data point, whether it is a customer profile or an image or a sentence in NLP, whatever it may be, it is actually a vector. Everything in data science is represented as a vector. Only then you can find the relation between two vectors and all those. Now, a vector is more than just a list of numbers, I'm saying. It has magnitude and direction, all that fine. In mathematical object that lives in a space where operations like addition, scaling, transformation all have the meaning, and all those functions when performed on the vector also lives in the vector space. Okay, you can imagine as a bigger playground in the universe where all the datas and vectors are residing. Okay, and that space where the vectors can like move, it can scale, it can transform. So all these operations are also being done in the vector space. Okay, now picture this like a vast invisible world, not just limited to 2D or 3D and all, which you can visualize it, but stretching across 100, 500, 10,000 or even more dimensions. Just imagine 10,000 dimensions of higher dimensionality in a hyperplane. So this space is empty at first. Okay, it doesn't have any vectors or any data in it. But as data arrives, it starts to fill with the vectors. And every vector we add has to follow some very strict rules. You cannot just add any vectors randomly. So these rules are called closure properties, and they are what give vector spaces their power. So let me explain. The first rule is a closure under addition. If you take two valid vectors in the space, two user profiles to be more specific with an example, and add them together, add two vectors. So as I told you, everything in data science, be it profile or be it word representation, embedding, whatever it may be, everything is represented as vector, we know. So user profile is also obviously represented as what? As vectors. We want to add them. The result should still make sense and be in the same space only. So addition of both the vectors should still be in the same vector space. It may represent an average profile or a blended behavior, but it must belong. Okay, so when you add up two user profile, what you are getting? You may end up with some average or common behavior, similarity between the two users, all those information you get. But still, I'm telling you, those behavior or those average between two user profile or you're getting some value as a vector only. So that vector will also belong to the vector space. So that is the first closure for addition. Now we are getting into the second rule. What is the second rule? Is the closure under scalar multiplication. Okay. Now I want you to take any vector and multiply it by a scalar value which doesn't have any direction. You know what is a scalar value, right? Maybe when you multiply a vector with a scalar value, what happens? I want you to imagine that. It can shrink or it can stretch, but it will not change the direction because it's just a scalar value only. It's not going to change the direction. It is going to still be in the same space only, in the same direction only. This idea derives gradient descent in machine learning. Okay, when you update weights, we scale a gradient vector and move it in the direction. That's a different story. So all these are all interrelated, you know. So for example, to elaborate this gradient descent, how you arrive at calculating the loss function is like you have a new weight. So basically what you do, you minus the old weight with derivative of the loss function. So what is the derivative of a loss function? So let's take a parameter theta, that's basically the weight, and then you're finding the derivative of loss function with respect to this theta, with respect to this weight. Okay, and then you're multiplying it with the scalar quality, which is the learning rate, and then with this quantity which you get, you're minusing with the old weight, then you get what? You get the new weight. So all this calculation, what is it doing? It is basically multiplying a vector with the scalar quantity. Okay, now the third rule is a closure under linear combination. I want you to imagine this as a linear combination means you multiply a vector with a scalar value, and then again you multiply another vector with another scalar value, and then you add them all, which also when you are adding those linear combination also results in what? Also results in the same vector space. So this you can imagine, you're multiplying a weight with the input. Okay, so this weight into, if you take like several vectors and scale them by different weights and add them together, the result should still lie inside the same space. That's what I mean to say. Okay, so x is an input and w1 x1 is one input and w1 is another weight. So you basically what you do, x into w1, then x2 into w2, and you're basically adding those, and still this summation results in what? The same vector space. This is the heart of like dimensionality reduction techniques in PCA. I want you to imagine there is a higher dimensional planes where the data points are all distributed. Now you have a wide spread of data representation, which is complex, which is obviously complex to calculate. So what you are doing is you want to reduce the dimension. To reduce the dimension, what you have to do? You have to find the PCA. So some problems, some real-time data sets require more PCA, like PCA 1 and PCA 2 or even PCA 3. It is subjective. So with this we are coming to the end of the linear algebra in data science. So the next part of the video will be part 2, which is probability in data science, the math. In the math part we are going to deal with the probability which is used in data science. So far we have seen about the linear algebra used in data science. So the part 2 math will be covering probability in data science. Okay, this is Lakshmi from the Skyverse Infinity Academy.